Hi, everyone. Um, Welcome to the first workshop for IEEE and HKN. We have a Discord. We're trying our best to get it more active. So if you guys use Discord, just join and have fun there. We also have Instagram for IEEE and HKN. And this is our Arduino Essentials virtual workshop. This workshop, I'm doing it as part of the robotics team leader. And if you like whatever you learn here, I encourage you to join our robotics team because we're gonna play with Arduino a lot. I wanna start by asking what is Arduino? And it's usually called a microcontroller, and that technically is not true since it's like a board that contains a microcontroller. But what it allows us to do is to read the inputs that we're given and basically program it in such a way that we can have the behavior that we want out of the microcontroller. Some examples may be, for example, a distance sensor. We're reading the inputs, and as soon as we detect a wall, we want the motors to rotate the other way. This is what a microcontroller allows us to do, is just to take the inputs and program the outputs in such a way that we decided to. Why use an Arduino? I mean, after all, there are so many other microcontrollers. Well, you know, there are many reasons why to use one. First is open source. Arduino gives us all basically the source code and the board view and everything. So people not only can program, okay, wait, give me 1 second. Sorry. Yeah, it's open source. This is great because not only we can see how it works, and we can basically, like, it allows us to also create our own Arduino boards since we know what makes an Arduino, and we have basically all the firmware and everything to create it. People are able to create Arduinos, people are able to create shields, etc. It has a large community, so if you're starting out, they're gonna be able to help you. You know, if you have any problems, you can Google it, and it's way more likely that you're gonna find a solution if you're starting out with an Arduino that if you're starting out with a microcontroller that is harder and has less of a community. It also has a ton of libraries, and that's great because most of the use that we get from an Arduino is, you know, the external modules.
I'm still friends with people that I started 18 years ago. They're still in the company as well. I know their kids. You know, I'm a little older in age, right? But, you know, I've been to their weddings and things along those lines. And so, you know, it's been a place for me. People have been.
Wait, sorry. I thought he had a question. Never mind. But yeah, you know, it has libraries. So if you want to use external OLED screens, or if you want to use whatever, you know, you can find a library, and that's gonna basically make the process so much easier. Yeah, someone has a question.
You mentioned before shields for Arduino. I was wondering what you meant by that.
Yeah, I got a little nervous in that part. You know, for example, today we're gonna build, and you're gonna see, we're gonna build a motor driver. And this is gonna allow us to control our DC motors in one way or the other. Now, we're gonna do it with a breadboard, and that takes a lot of space. A shield is like an external PCB that you can basically put on top of the Arduino, and that's gonna allow you to do the same functionality, but way more compact. I'm gonna Google some images here. So, well, if I can. Oh, sorry. Arduino shields. So, you know, you see how it has like the pins. This is, for example, Ethernet. Arduino Shield. And if you connect it, it's already pre-wired in such a way that you just have to put it on top of your Arduino, and then you can connect an Ethernet cable to it. That's why being open source helps a lot, because people are able to design these boards easily since they know everything that takes part of an Arduino, since they have all that material. I hope that answers the question. But yeah, we have the libraries. It's a simple programming environment, because if you ever try to program a microcontroller, you basically have to do it with C, and that can get really involved very quickly if you're just starting out. Arduino makes it simple by creating their own language, programming language that is way easier, and we're gonna see it today. It also is multi-platform, so you can use it with a Windows computer, a Linux, Mac, whatever you have, and it's USB programmable. You just plug it to your computer and you can program it. And finally, it's inexpensive. Due to it being open source, basically clone companies are able to create Arduinos fairly cheaply since they have all the schematics and everything. So you can buy an Arduino Uno and get it shipped to your home for less than $5 if you buy a clone. And that's really useful because, you know, we're college students and we want to create prototypes. Well, we don't want to spend a lot in doing so. You can always, if you want to help, you can always donate in their website. So this is the GPIO for the Arduino Uno. And if it's your first time seeing it, it may be a little bit scary, but in reality, it's not that bad. We have the right side, which is basically the digital pins. It goes from D0 to D13. The digital pins are, as they say, you know, as their name says, they are digital. So they can be set to either zeros or ones. And some of them, the ones that have the tilde, can be set to a PWM signal. I'm gonna explain more about PWM signals later on, but for now, just know that the right ones are the digital. Here we have analog pins, which allows us to read analog signals, for example, a potentiometer. And we have the power pins. This allows us to power up external modules that we may have. The Arduino has a 5 volt, a 3.3 volt, ground, and voltage in, that's if you wanna power the Arduino from an external battery or something. We also have, and I have a few important notes, only some of the digital pins can create PWM signals. For example, here we see the digital 3, 5, 6, 9, 10, and 11 are the ones that can create PWM. Analog signals can read analog pins can read analog signals, but they cannot write it because our Arduino is a digital device. We cannot really create analog signals that way. We can get close by generating PWM, but we cannot really write actual analog. An interesting fact is if you're running out of digital pins, you can use the analog pins as digital pins too. That's no problem. And the Arduino supports a few communication interfaces. For example, serial communication, I2C, and SPI. This is really useful because some modules, for example, mostly screens and stuff like that, they rely on communication interfaces like SPI in order to be able to send a lot of data without having to take up so many pins. And you can also use I2C for cool things like communicating between two Arduinos. For example, if you have a project that you're running out of pins and you need more pins, you can get another Arduino and communicate between them using serial communication or I2C. You also have a built-in voltage regulator. It's right here. Let me get the pointer. But yeah, you can, if you want to power your Arduino from an external power source, this takes, I believe, from 6 volts to 12, or I haven't checked that very well, but it's around that part. And since it has here a voltage regulator, you can power it on like that from a battery or whatever. That makes it very useful for robotics projects. What are we gonna learn today? And I wanna take an approach, instead of just teaching the basics, I wanna get hands-on and learn by creating different prototypes. So first we're gonna play with LEDs, potentiometers, and servos. And this is gonna teach us the essentials of Arduino programming, digital signals, analog signals, PWM signals. Then I'm gonna introduce an ultrasonic distance sensor. We're gonna see how it works, how to read the data, how to perform calculations with the Arduino, and how to print statements with serial.print. And finally, if we have time, I hope, we're gonna work with DC motors, how to control them, what are the drawbacks of using DC motors that we have to overcome. We're gonna set up an H-bridge motor controller, sorry, and encoders. I don't think we're gonna have time to work with that, but that can be like an extra activity that if you really are interested in seeing how motors work, you can try that later on by your own time. Don't worry if some of these topics seem a little bit new to you. We're gonna go over them. So yeah, let's start by a simple LED blink. The functionality that we want out of it is to, oh my God, sorry, you guys have questions. Oh, never mind. Yeah, we want to have the simple functionality of it blinking on and off with 1 second intervals. And we're gonna introduce the following terms: setup, loop, digital write, and delay. So this is gonna be a good opportunity to introduce the tool that we're gonna use, which is Tinkercad. It's commonly known for creating 3D models, but you can use it to simulate circuits. So just come here and create an account. Or you can click sign in and you just use your Google account. That's what I do, and it's easy. So I'm gonna wait a little bit for you guys to be able to log in with your Google account. And here you see some 3D designs that I have made, and then you have circuits. Now, Tinkercad loves creating weird names. And since I don't change them, yeah, there they are. But once you create your account and log in, you just go to circuits and create a new circuit. I'm gonna wait for a little bit so all of you that are trying to do this can also follow. But yeah, if we see here, we have basically our playground. This is where we're gonna put everything. Then we have like a code option, a start simulation option, and then we have a toolbox. Now, I'm gonna set it to all because I wanna see all the elements. And this is what I mean with this tool being great for starting out. Look at all the stuff that you got to play with. I mean, if you're interested in learning Arduino, I think you don't even need to buy one. You just need to, come here and play around. It's really interesting. So let's just search for an Arduino. I'm gonna click it and I'm gonna put it here. So here we have it. It's basically what I showed you guys. We have our pins from 0 to 13, and then the analog ones, and then our power pins. Now I'm gonna add an LED. Oh God, here, LED. Right? Finally, we need a resistor to use with an LED. If not, it's just gonna burn. So the way that I'm gonna connect this is The cathode is going to ground. The anode is going to the resistor and to pin 13. We're going to control this LED with pin 13, right? So here we go. I'm gonna try my best to color code the cables throughout the whole workshop. So yeah, how do we control this? Well, first let's go to code. We click the Arduino, go to code, and then you see this that looks like Scratch. We don't want that. You click blocks and then text. Continue. This is gonna allow you to program it just like you would program it with the Arduino IDE if you had an actual Arduino. This is why I like this tool so much. We're not gonna miss out on anything. They give you an example code. We're gonna remove it for now because I wanna explain. And someone has a question. What do you, okay, the new Arduino design. You basically go to Tinkercad. You go to circuits and create a new circuit. I hope that helps. You click create and it's gonna create. Let me know if your question was something else. Let's change the name actually, because IEEE workshop. Right? So we came here, we added our LED, and we're gonna program it. Remember how the pins, you know, these are called GPIO, general input and output. We need to tell the Arduino if we wanna use the pin as an input or as an output. And we're gonna do this in setup. Setup happens once in the beginning of the code, and loop happens indefinitely after the setup. So if we use the function pin mode, then we set the pin, we tell it the pin number and then the mode that we want to use. We want to use pin 13 as an output. This is going to output the signal to turning on or off, right? Then how do you actually set a pin to be high or low? Well, you use digital write. Then you put the pin number and then high. So this is gonna turn it on. This is gonna turn on our LED. In fact, if we try it right now, our LED is on. But I want it to blink, right? So if I want it to blink, I want it to go on and off. So digital bright 13 low. You can see how we use the words high and low. That's basically because these are digital pins and you have two states, 0 or 1, high or low. Now, if you just do this right now and you try it, it's not gonna blink. What's gonna happen is it's just gonna stay on. And that's because this is happening so fast that the LED is, you cannot see it turning on and off. What you need to add is delays. We're gonna add 2 delays, right? What these are gonna do is basically, we're turning on the LED and then we're gonna wait for a certain amount of time and then we turn it off and then we wait again. So the delays work with milliseconds. If you add 1000, this is gonna be the same as 1 second. And if you add 1000 here, this is gonna be the same as 1 second. I'm gonna do it just for showing, to turn it on and then turn it off for 2 seconds. So it's on for 1 second and it's off for 2 seconds. I hope you guys can see that. So yeah, this is our first. It's pretty simple. It's nothing special, but I think it's a good way to get started and learn how to use the digital pins to send signals. So, okay, we send digital signals, but what if I wanna, what if I wanna make my LED, for example, fade, right? You know, I don't like my LED being on and off. I want it to fade with a smooth curve. So that's where we can start seeing PWM signals. And as it says here, PWM signals is basically a technique that we use to create analog-like signals out of digital pins. Since at the end of the day, our Arduino is a microcontroller, and microcontrollers work with binary logic. They can either be 0 or 1. We don't really have the possibility to create analog signals out of them. So the closest that we can do is PWM. And if you see it here, you know, if we have a PWM signal of 0, it's basically like a digital signal of 0. If you have a PWM of 1, it's like a digital of 1. But then again, if you have a PWM signal of half, which is basically like it's turned on by half the time and turned off by half the time, this signal is going to act as if it was a 2.5 volt signal. It's not going to act as if it was a 5 volt. If you turn it on for 25% of the time, it's going to act as if it was 1.37, and this is going to act as if it was 3.75. So since LEDs, they are going to adjust their brightness depending on the voltage that we give them. By using PWM signals, we can adjust the intensity of the LED by changing the range. Sorry, by changing the Dory cycle. I hope that wasn't too confusing. I'm bad at explaining PWM, but you have to know that our Arduino supports PWM signals out from 0 to 255. And this is because it has an internal clock that works with 8 bits. And you know that 8 bits have a maximum amount of combinations of 256 numbers, which is why this is this way. And funnily enough, even though we're creating PWM signals, the function to use them, to create them, is called analog write. Even though we're not really creating analog signals, that's the function that you use. It's like a fun fact. So basically, if you put analog write of 0, you're gonna have this. Analog write 64, you're gonna have this. And then analog write to 55, you're gonna have this. So yeah, let's stop talking and let's start developing it, right? 1 second. So I'm gonna get rid of this for now. If I do analog write and I set the pin and I set it to 255, let's do something. Instead of having to write the pin number, let's define the pin number. Define LED 13. This is gonna allow us to not have to write the pin number again. If we change the LED to another pin, we just have to change this number instead of having to change the whole code. So that's, that's better for long term. If we do analog bright, the LED to 255, you're gonna see it's gonna turn on full brightness. If we change it to 125, and let me change the resistance, because LEDs work better with a 220 resistance, at least with this simulation. Okay, never mind. Let's see something. Okay, so what you're seeing here, basically the LED is not turning on due to the resistance of the resistor. Since we're sending such a low signal here, let me try something. Okay. Let's do the fade instead. So to create the fade, the way that I thought about it is using a for loop. We're gonna start with the brightness. you know, the way the for loops work, you have a variable, then you have a condition. Brightness has to be less than 255. And then you have an addition at the end, or you have an operation at the end, right? So at the end of every for loop, we're gonna add 5 to the brightness. So instead of manually setting the value for the LED with the analog write, I'm just gonna analog write the LED, and then I'm gonna set it to be the value of the brightness. So if you see what's happening here, the brightness is gonna go from 0 and it's gonna add 5, 5, 5 out to the point that it gets to 255. And then the for loop is gonna stop. So this is gonna fade from 0 to 255. And I'm gonna add a delay between each step of 50. Now this is going from 0 to 255. Now I wanna go from high to low. So I'm gonna copy the for loop. I'm gonna change this to be negative. I'm gonna start at 255. And I'm gonna say that this has to be greater than 0. So it goes from 0 to 255 and then from 255 to 0. If we simulate this, let's see what happens. You can kind of see how it's fading away and fading in. It's hard to see it really with the simulation tool because it's a little bit finicky with PWM. But that's the idea. I mean, we're changing the value of the brightness from 0 to 50 to 55 with the gradual granularity of PWM. Yeah, that was a really bad example, but I think as we keep going and we keep playing with PWM, it's gonna make all more sense. So let's try reading an analog signal. Well, we have a potentiometer, and the way it works is if it's set to one side, you're gonna, for example, this potentiometer is gonna take 5 volts and ground. So when it's set to one side, this pin right here is gonna basically send 0 volts, and then when you set it to all the other way, it's gonna be 5 volts. So any value in between is gonna be a number of volts in between 0 and 5. How do you read that? Imagine you wanna create a volume knob or something. You would wanna use a potentiometer, and for example, an Arduino will be great for that. So yeah, let's try reading an analog signal. Okay, so let's just get rid of the LED. I press Shift and I click it. Or you can also click the LED and the elements and you can get rid of them that way. I'm gonna delete the code that we have. Right, so basically we're clean again. If we press the code button, you're back to the place where you can select the components. So here I want to select a potentiometer, and I press the R to rotate it. You don't have to rotate it, but it just makes it look better, I guess. I'm gonna connect the two external pins. One is 5 volts and the other one is ground. I'm gonna do it black. And then finally, the middle pin. And we can select whatever pin we want. I'm gonna put it to be orange. So let's try and read the analog signal from this. Well, first, remember how I told you guys that since we have IO pins, we need to define the pin that we're gonna use? Well, since the analog pins cannot really create analog signals, they just create digital ones. They just read analog signals. You don't really need to define them. So that's like a step that you can miss. Basically, you use analog read. We're gonna set the pin to be A3, A3. And I wanna create a variable, reading. I wanna create a variable, right? So let's go back to here. What's the functionality that we want? Well, we want our Arduino to read the analog signal out of the potentiometer and then print it. So we already, with this, we are able to read it every time the loop happens. I'm gonna delay it because the simulation performs better when you delay in between. So if I wanna print something, you can print stuff with Arduino using serial.print. And at the end, I'm adding ln because that's gonna allow us at the end of the thing that it prints, it's gonna go to the next line. So it's gonna look better in the console. So if we print the reading, you're gonna see that nothing's gonna happen. This is because we need to actually define the serial. So you define the serial as serial begin and then the baud rate. For now, you don't have to worry about this. Just set it to 9600, and that's a very common rate. And now if you see how by changing the potentiometer, the values go and change. I don't know if you remember the PWM signals, we set them from 0 to 255. Why is the analog signal reading from 0 to 123? Well, that's because the analog to digital converter in the Arduino is 10 bits instead of being 8 bits like the PWM clock. So since it's 10 bits, it reads from 0 to 1023. This can be a problem though. For example, if you wanted to read an analog signal and then you wanted to change something that uses a PWM using our reading input, that would be a problem because our numbers don't go from 0 to 255. There's actually a function called map. And let me see if I can get there. Arduino map. This function allows you to change, like for example, this will be our reading value. This will be the first like from 0 to 123, and then we set the limits that we wanted to have from 0 to 255. So yeah, that way you will be able to do that, and we're gonna see that in the servo motor example. But for now, we basically were able to read an analog signal. And here you have the code, and here you have the results. So yeah. Yeah, this is just showing more or less the process. You know, we have our analog signal from the potentiometer. The Arduino reads it and converts it into basically values. And then if you want to change it back to being an analog signal, you have to do a PWM, and then you filter it. And this is the code. What if I want to add a servo motor? I want to add a servo motor, and I want to be able to control the rotation without potentiometer. To do this code, we're going to actually use a library. Arduino has a servo library, and that's just going to be one example of why Arduino is so great, because for developing stuff like this, you don't really need to know the ins and outs of how everything works. You just need to use a library. This is more or less like what's inside of a servo motor, and it's basically a DC motor with a gearbox and a potentiometer. Why does it need a potentiometer? Well, servo motors are not like regular DC motors. You set them to an angle. For example, this one goes from 0 to 180, and the potentiometer is the one basically reading the angle. So yeah, I'm gonna rotate my potentiometer and I wanna set the angle accordingly. So let's do that. How do you add a servo motor? Well, let's go here and servo. Let me see if there are any questions. Okay. Here's the servo. You see 3 pins. You have voltage, ground, and signal. I'm gonna connect the voltage straight here. And yeah, this is really ugly. I'm gonna try and make it better. We have our voltage here. And I'm gonna set it to be red. Then we have our ground. And the ground is going to the ground, of course. It's black. And then finally we have the signal pin. Now, you have to know, servo motors, the signal, this signal right here is being set with actually another time again. It's set with a PWM signal. And you know that only a few pins on the Arduino actually work with PWM. So if I did this same, oh God, if I did this same sketch and I connected the servo motor to pin 2, for example, it wouldn't work and you wouldn't even know why. Well, that's why, because you're not able to send a PWM signal through that pin. So we need to make sure we use a pin that supports that. Someone has a question. Does it tell you which voltage? Okay, let's see. Ground, power, and signal. Yeah, it tells you. But usually all these modules like color coding, and you can see here, I mean, it's really small, but the middle one is red and the other one is brown and this one is orange. So yeah, I connected that to 5 volts, connected the other one to ground, and connected that to pin 3. I hope that answered your question. So let's use the same code that we used before, but now let's add the servo motor. That's gonna be interesting. Let me just give me 1 second. Okay. Well, what's going on here? We're defining our serial so we can see the value. We created a variable and then we are assigning it to the value of the potentiometer and then we're printing it. Now, if I want to use the servo motor, I need to include the servo library. So let's include the library first. You first include the library, then you need to create a variable, pretty much. When you're using the servo library, you're gonna have to refer to this object instead of the servo itself. You're gonna see it now. But basically, first, you need to my servo dot attach. And then you set the pin for the servo. Our pin is pin number 3. Someone has a question, sorry. On an actual board, will both pins from the servo. Okay. A servo motor, if you're using a small one, like this one, you know, the blue ones that are used in RC and stuff, that's totally fine to connect it to the 5 volts. But as soon as you start getting into more power hungry devices, you know, more power hungry servos or actual DC motors and stuff, you really shouldn't be connecting it to the Arduino 5 volts. And that's a great question. I didn't go over that. If you're just using one servo, that's fine. If you're using more than one, it's completely cool to have an external power source. Oh, never mind. Well, I'm gonna show you something. In an actual board, you wouldn't be able to connect them. I just did it because it's easier that way here, but you would need to use a breadboard like this. And I'm gonna more or less go over. Yeah, exactly. I got it right. Big brain. The cool thing about breadboards is, well, I'm gonna hover over the little pins and you can see the negative pin, all of it is connected. The positive, all of it is connected. And then every single row is connected in such a way. So if you connect something here, it's the same as if you connect it here. Let's change this whole diagram and use a breadboard because that's the way that it should be done. I was I was kind of lazy. So yeah, let me move the breadboard here, and I'm gonna press R to rotate it. You connect the 5 volts here. And then you connect the ground here. Of course, so it's easier, let's change the colors. Black. And other thing that you can do is, so you have the power in both sides. You can connect them together. We're not really gonna need that, but sometimes you need both sides to have the power. So that's how you do it. So now I have my potentiometer connected to pin A3. So let's find a potentiometer here. Imagine I set it on in the board like that. The middle pin is gonna be the signal pin. So I'm gonna move the middle pin to be A3. Then this pin right here is gonna be voltage, and this is gonna be ground. You can see how everything in this row is connected, and then everything in this row is connected in such a way. You have to have that mental image, and then breadboards become so easy after seeing that. Oh, there are more questions. Oh God. Efficient with your time. Yeah, right. I'm efficient with my time all the time. Orange. That looks better even. So let's use a servo now. In the case that you needed to use stuff that needed more power, imagine you end up using an external battery. For example, a 9-volt or a potato battery. What the fuck? Okay, let's not use a potato battery. You will need, that the batteries, this one is rated for 9 volts, and actually is rated for 9, but as you use it, the voltage is gonna drop. It's gonna have from 9 to, for example, 7. Well, your modules, they are very picky. They all need exactly 5 volts. So you will need to actually connect your 9-volt battery to a voltage regulator. You have 5 volts ones, and you have 3.3 volts ones. I'm not gonna go over how they work, but that's how you would do it. They basically are like magic. You connect a voltage source within the specs, and it's always gonna give you the voltage that you need for the modules. and you're not at risk of burning out your board, for example, using too many servo motors or whatever. So yeah, let's connect this here. So the power pin, I'm connecting it to positive, this one to ground, and this one to pin 3, which is PWM. Okay, let's go back to the code. I included the servo library. I created my servo object. Then I initiated the servo by using this is all, like you see this by searching like basically servo library, and all those methods and functions, they are given here, attach, write, etc. So you just need to know which library you're using, and then you can research it online so you can know how to use it. But yeah, we're attaching it, and to move the servo to the direction we want, we just put the name my servo dot right, and then we set the direction that we want it to be in angles. For example, 0 angles, 0 degrees. Then I'm gonna put a delay of 2 seconds. Then I want it to go my servo dot right 180 degrees, and another delay of 2 seconds. So what you're gonna see now is by running this, hopefully, the servo goes from 0 to 180 to 0 to 180. Why? Because this is repeating. 0, 180, then repeats, 0, 180, repeats. You know what I mean? And we also have, well, this should be working. Oh, it is. It's just low because we have the delays. We have the potentiometer giving us readings. Now, I don't want this to move just by itself. I want this to move with my, with my servo, sorry, my potentiometer input. So let's change the code a little bit. I have my reading, which is analog read, and this prints values from 0 to 123. What if I come here and I set my servo dot write, and I use my reading? It's not really gonna work because the angle is not going from 0 to 180. It's going from 0 to 123. So it doesn't really work as we want it. But if I instead use the map function that I kind of showed you already, you first put the variable that you're changing, reading, then the first boundaries of that variable, which is from 0 to 123, then the boundaries that you want from 0 to 180. And what this is gonna do is it's gonna map the values from this to what we want. And if we do it now, let's see what happens. As you change it, the servo is changing. That's pretty cool. Now, you can see how it's working kind of like backwards. And well, an easy fix, a lazy fix is just to flip around the values here. I change it to 180 and then here's 0. And you're gonna see how it basically follows. So yeah, that's how you control, for example, that's how you take analog signals from a potentiometer and then you can write them to a servo motor. This can be useful, for example, if you have a robotic arm that uses servo motors and you want to be able to program it. Well, you can put potentiometers within the extreme, within the joints, And then the potentiometers are gonna give you the location. So you can basically move the arm by itself and record all the locations, and then you can set it to move without you touching it, and it's gonna move to the same places thanks to the potentiometer reading the values. So that's one of the uses that you can have for that. It's hard to see here because we're in a simulation, but yeah. Let's see if, let me hurry up because then we won't have time. Now I'm gonna introduce something that I find really cool, which is an ultrasonic distance sensor. And apparently I forgot to add the terms introduced, but that doesn't matter, right? So we're gonna create this sketch and it's gonna be able to read the distance of an object that is in front of it. That's our goal. However, before that, I think I need to explain to you more or less how this works. And an ultrasonic distance sensor sends ultrasonic waves, and the time that it takes them to bounce in the object and come back to the sensor is what we use to calculate the distance. So you have 4 pins here. Voltage, ground, those are pretty common. Someone has a question. Thank you so much for the workshop. Okay. No worries. I'm gonna upload it to YouTube, so it's gonna be there. We have the trigger and the echo pin. Basically, the way this works is the trigger pin. You send a pulse to the trigger pin of 10 microseconds. Then the sensor will send 8 ultrasonic pulses, and the time that it takes to receive it, you can use that to calculate. It doesn't make a lot of sense now, but let's see it with a diagram that I created here. So you have your ultrasonic sensor, right? You send a 10 microsecond pulse to the pin trigger. That's gonna enable it to send the signals. So right now it's transmitting the 8 ultrasonic waves. It's gonna bounce on the object, and once it comes back, the echo pin is gonna be triggered for the length of the time that it took for the whole thing to travel. So yeah, I hope that makes sense. Ultrasonic waves travel at the speed of sound. So if we know the time that it took the wave to move, since we know that the constant of speed of sound is 343 meters per second, or 0.0343 centimeters per microsecond, you can calculate the distance just like that. And we're gonna go over that right now in the sketch. So yeah. Also, since you have, the signal traveled there and then you had to wait for it to come back, the actual distance you have to divide the time that it took by 2, because you're traveling twice basically. So yeah, let's program it. So sadly, let's get rid of our thing. Stop the simulation, shift, click, and just select everything. If you want to keep it, you can create a new sketch instead of deleting this, but I'm gonna delete it. So yeah, Arduino. We're gonna add an Arduino distance sensor, and there are actually 2 types. They are the same in essence, but for now we're gonna use the 4 pins, and I'm gonna explain what's the difference between the 2. So here we are again. We have our VCC, our ground, our trigger, and our echo. So VCC is voltage, and this module takes 5 volts. So we're gonna connect it here. Ground. Right? Then the trigger. this can be set since, I mean, we saw it already. The trigger pin and the echo pin, those are just digital pins. They go up and down, up and down. So I'm gonna set this to be pin 2 and this one to be pin 3. No preference, I just chose 2 random pins. Yeah, my OCD is killing me. The ground here, let me put it black, yellow, and green. I hope this makes a little bit of sense. So for the code, if you're interested, let's delete the default code that they add. One second. Okay. First, let's define our pins. We have our trigger pin, and the trigger pin is number 2. Then define our echo pin, and this is number 3. We want to use the serial console to see the distance. So I'm gonna start the serial by doing serial begin 96. You have to do this every time that you want to print a serial command. Yeah, Juan, ask.
Do we need a library for these two?
This, actually, you don't need a library. Since I show you, we can basically, we're gonna program it without a library. And you're gonna see how. So for now, yeah, we define the pins. We're saying that we wanna use serial. And we also need to define those 2 pins, pin mode. Sorry, it has to be like this, pin mode. The trigger pin is gonna be output, since we are outputting a 10 microsecond signal, and the other pin, echo pin, is gonna be input, because we're receiving the signal. We're gonna see that, like, we're using the signal that we received to calculate the distance. So, okay, we define the pins, and let's go ahead and do the code. And for this, I'm actually, I think it's better if I do this. I hope you guys can see it. Kinda. I'm gonna make it bigger. Okay, that's too big. Yeah. So the first thing that we're gonna do is we're gonna set the trigger digital right. We're gonna set the trigger to low. You know, we're starting the signal. We wanna make sure it's low. So trigger pin low. Since, okay, then we're gonna wait a certain amount of time. Now, since all of this is gonna happen in microseconds, we need to use the function called, instead of delay, is delay microseconds. I'm gonna delay microseconds for 2. Then we need to set it to be high for 10 microseconds. So digital bright high and trigger pin. 10. And then we set it again back to low. Now, what do we do here? We basically just did this right here. We started low, high for 10, and then low again. What do we need to do now? Well, we should record the length of this echo signal that we're gonna receive. So I'm gonna call it a double variable. I'm gonna call it duration. And we have this function called pulse in. And what it's gonna allow us to do is it's basically gonna be watching over the echo pin. And as soon as it gets high due to the transmitted signal receiving, coming back to the receiver, it's gonna record the amount of time that it took in microseconds for it to go from high to low again. This is, I didn't explain it well, but you know, we have a duration, and for example, here the duration is 500 microseconds. If it takes 500 microseconds for the signal to travel, this pulse-in function is gonna tell us, because it's just gonna tell us the amount of time that this stayed as a high. And finally, we need to calculate the distance. And for this, we use the formula that I showed you before. We know that, well, it's a little bit small, but we know that, I hope it's not too small. I'm sorry about that. Yeah, we have the distance. So it's basically gonna be the duration over 2 multiplied by the constant of time, sorry, of speed of sound. And if we print this, serial.print ln is just to print in the next line, distance. We're gonna see that what happens here. So yeah, we set it to low, high for 10 microseconds, then low again. Then we recorded the pulse, and then we're using that recorded value, which is the time that it took, in order to calculate the distance, since we know the speed of sound. It's a little bit complicated, but that's basically how you use a ultrasonic distance sensor. And if you see it now, the sensor, the object is at 113 centimeters, and our sensor is reading 111. It's never gonna be perfect, but it's close enough to 15, and we're reading to 12. So yeah, that's a cool way to do it. I believe there's also a library for this, but it's such a short code that it's not really needed to add a library. I hope that was understandable. So that's how to use that's how you use a ultrasonic distance sensor. I'm gonna actually, because I told you guys that I was gonna tell you the difference. There's another kind of ultrasonic distance sensor, and it's this. The only difference that they have is instead of having a trigger pin and an echo pin, it just has a signal pin. And in reality, what's happening is inside of the board, they just did this. They connected the pins together. So they both act like the same thing. How would you use that instead of this? Well, let's try it. Let me just try and use this instead of the other one. Signal to 3, and then 5 volts to 5 volts. You know, that's just something that may seem confusing at the beginning, because you don't know, what's the difference between them. Well, basically, in the code, what will change is, instead of having to define the pins here, first, both pins are the same. They are both 3, right? This is 3 and this is 3. And now instead of having to define the functionality of them there, you basically have to set it here, pin mode, trig pin to output. So the trigger pin, which is pin 3, is set to output. And then after you use it for the output, you basically have to do the same, but now echo pin, which is also 3, input. Basically, you have to change the functionality of the pin on the fly. But that allows you to be able to use the sensor with just 1 pin instead of 2. And if you have to use, for example, 8 ultrasonic distance sensors, it really starts becoming troublesome to have so many pins used. So this way, you can save yourself a pin, and that's pretty cool in my opinion. Yeah, you just change the pin mode on the fly, and this will be the same as just writing 3 and 3. And let's test it out and see if it works. It works just the same way. See, we just save ourselves a pin that way. Cool to know. Now I'm gonna delete it because we're gonna go to the last project that we're gonna make. And this is a DC motor. We're gonna start running a DC motor. Why use DC motors? Well, they are pretty popular for being cheap. They are cheap for the amount of power that they provide. So that's why they are pretty much commonly used in RC cars and even some, well, it's just, if you can use them, it's better because they will allow you to have a motor for a cheaper price, and it's gonna be, I don't know how to explain this. Never mind. How do they work? Well, you can see here they have 2 magnets, and those are 2 poles, and then you have a coil, 2 coils on the inside, and then you have the brushes touching. Basically, you send a voltage to the brushes, and that's gonna create an electromagnetic field inside of the motor, and that joined together with the outside magnets, that makes it rotate. If you put the voltage, the positive here and the ground here, it's gonna rotate one way. If you put the positive here and the ground here, it's gonna rotate the other way. So if you wanted to have a car that goes forwards and backwards, that means that you would need to physically disconnect the cables and then switch them and connect them back. That's just insane, in my opinion. That's one of the problems with DC motors. And that's one of the things that we're gonna overcome here. Another thing, DC motors usually translate velocity linearly with the voltage that you give them. If you give this motor 3 volts, it's gonna go slower than if you give it 6 volts. If you're just connecting it with a battery, you have no way of controlling the speed either. And finally, another problem that we're not gonna touch on here, but it's also important when using DC motors, is no DC motor is created equal. They all have differences. And even if you have 2 DC motors of the same model, one is gonna end up being faster than the other one. And if you have, for example, a robot where you rely on it being precise, that it goes in a straight line, you cannot really rely on that if one motor is faster than the other one. It's just gonna start shifting to one side. The way to overcome this is with encoders, and I'm not gonna go over them because it's a little bit more complex and it's gonna take time, but it basically checks the speed of the motor in real time. By doing that, you can basically make up for the differences in speed between each motor in real time. And that way you can ensure that your robot is always gonna go in a straight line. But for now, let's just focus on how to change the direction and how to change the speed. And to do that, H-bridge circuits are very popular. Imagine this is a motor, right? If I wanted to rotate one way, imagine I connect this side. So now this side is positive and this side is negative. It's gonna rotate this way. But if I switch the switches, now it's gonna rotate this way because this side is positive and this side is negative. So just by doing that, we were able to change the direction on the fly without really having to physically move the cables. And there are pretty popular H-bridge circuits out there. This is one of them. I just see it a lot on kits and stuff for DC motor cars and stuff. It's basically a glorified H-bridge, and you connect the two motors over here and here, and it allows you to have control of the direction and the velocity. However, sadly, Tinkercad doesn't have that module for us. Oh wait. Tinkercad doesn't really have that module, which is really easy to implement. However, they have an H-bridge, and if you search it here, H-bridge, okay, sorry, motor driver somewhere here. It's a tiny little thing. I'm gonna try and let's just go ahead and use this with a breadboard and the schematic. And this is kind of like a good example of what you're gonna have to do sometimes when you're prototyping with Arduino. It's never just gonna be just modules and everything's gonna be perfect. Sometimes you have to, you know, do more ugly things and see it. I look at the schematics and stuff. I mean, we're engineers, right? So this is the schematic for the H-bridge. And as you can see, this allows for two motors. For now, we're just gonna use one motor, which is the left side. You have the enable pin. And this takes a PWM. Basically, the PWM, the value that you give it is gonna determine the speed of the motor. If you give a PWM of 0, it's gonna go off. If you give it a PWM of 255, it's gonna be a full speed. Then you have the input. And then you have two inputs, input 1 and input 2. You're gonna use these inputs to control the direction. Then you have the motor, and then you have ground. So let's wire this. And I'm gonna try to have it here next to our Arduino. I hope you guys can read that. Man, that really is small. Well, since we're only gonna use the left side, let me make it bigger like that. So yeah, let's add we have the motor driver, the H-bridge motor driver. Then we're gonna add a breadboard here. I'm actually gonna select everything and press R to rotate it. Now, these two pins, they go to ground. No, never mind, those not. The middle pins go to ground. Let's add a motor here. DC motor. That pin and this pin, those go to the motor. Black. The motor, I'm gonna put it green. No, yellow. As you can see, the pin number 2 and 7, those go to the Arduino. So let's add an Arduino here. So yeah, I'm gonna go ahead and get this pin out. So yeah, we just wired the input pins to the microcontroller. And finally, we need a PWM input here. Yeah, this will be so much easier if we had the motor driver module. That's why Arduino is so great, because you have all the modules. Finally, you need to give voltage to both this pin and this pin. So let's just connect that to 5 volts and connect this to 5 volts. I'm gonna go ahead now and color code everything. Blue, orange, orange, and then, yeah. Okay, sorry. Let's connect the voltage to here and the ground to here. And I'm gonna go ahead and connect this voltage to the other one and this ground to the other one too. And then we're done. Yeah, we did a huge thing here. Okay. The way the H-bridge motor drivers work is you have the 2 input pins. If I have my input pin number 1 set to 1 and the other one set to 0, it's gonna move, the motor is gonna move one way. If I have it the other way around, it's gonna move the other way. So what you do in this case, let's just create the code for it. And this is the same way that it works with other modules. You just wouldn't have to use the breadboard. Let me define the enable pin, which is the one that has the PWM signal, the blue one. And that's fine, 5. Then let me define the input pin number 1, input 1 to be 3, and then define input 2 to be 2. That's all we need now. So we set the pins in 1. They are both output. Actually, we also need to set the enable pin. Okay. Finally, we have the loop. So let me just show you what I told you. Like, first, you know the enable pin, if it's a PWM signal, whatever value you give it is the speed of the motor. So I'm just gonna go ahead and analog. Since it's a PWM, we use analog write, enable, and I'm gonna have it be full speed. Then Then we have the other two pins. Pin 1 is going to be high. Sorry, input 1 is going to be high and input 2 is going to be low. So if you see this right now and you run it, of course we have to run it after all that work. We made it, the motor turns. So the analog, right, the enable pin, we're setting it to full speed. If I set it to 150 instead of 255, 150, for example, you can see how it's rotating at half the speed. So yeah, you can basically control the speed by setting the enable pin to whatever value you want within 0 and 55, 255. And then finally, you control the direction with this. So we have, if I wanted it to go the other way, I would just shift this, low and high. Now, of course, we like to add delays so we can see it changing 2 seconds and then other 2 seconds. And finally, I think this is it. It goes one way and then it changes. We were able to grab a DC motor that by itself is really not useful at all because we cannot really shift it or set the speed. And instead, by using a H-bridge motor driver, we're able to control the direction and the speed. So that's pretty useful for robotics projects, for example. And I think this is it. I think we all made it till the end. So yeah, thank you for watching. Let me get there. Thank you for watching.